For a long time in artificial intelligence, there's been this big, almost legendary quest to create a single AI that can just learn to do pretty much anything we throw at it without us constantly needing to go in and manually adjust a million different settings.
Yeah, it's really about moving beyond these very specialized AIs that can do one thing incredibly well, like playing a specific game, but, well, fall flat on their face with anything else. The dream is a more adaptable general intelligence.
Exactly. Think about it. We've seen these amazing AI breakthroughs, whether it's conquering Go or dominating complex video games. But the tricky part is the algorithms behind them are usually tailor-made for that exact problem. They're brilliant at that one thing, but try to repurpose them for something even slightly different, like controlling a robot arm, and they're often completely lost.
Uh-huh.
Well, today we're diving deep into some seriously interesting research that feels like a major step towards this idea of a more general AI. We're talking about a new algorithm called DreamerV3 and the paper that describes it. Mastering diverse control tasks through world models.
And what's so compelling about DreamerV3 is that it has reportedly mastered over 150 different tasks. That's, a huge leap in versatility, covering everything from classic Atari games and intricate robot control to even figuring out how to collect diamonds in the incredibly complex world of Minecraft.
Wow.
And it did all of this starting from nothing.
From scratch. That's what really grabbed me. Minecraft isn't some simple linear game. It's this massive, open environment with endless possibilities. And finding something rare like a diamond can take a long time and a lot of strategic thinking.
Right.
DreamerV3 had to learn the whole process, the long-term planning, just to get to that diamond. And this deep dive, just for you, is all about understanding the core ideas behind how it achieves something so impressive.
So we're going to break down the fundamental concepts that made DreamerV3 different and try to understand why its achievements signal, well, a significant shift in the field.
Oh.
We'll focus on the main ideas without getting bogged down in overly technical details.
To really illustrate how adaptable this algorithm is, the researchers put it through a gauntlet of challenges. We're talking about teaching robots to walk and manipulate objects, mastering a wide range of Atari video games just from looking at the screen, navigating these constantly changing, procedurally generated environments, tackling complex tasks in these 3D simulated worlds called DMLab, and of course, conquering Minecraft. It's a really impressive resume.
So our goal today is to answer this fundamental question. How can a single algorithm become so proficient at such a wide variety of tasks? It's a shortcut to understanding a really exciting advancement in artificial intelligence.
Okay, let's unpack this, because when we think about how reinforcement learning, or RL, the underlying technology here, has traditionally worked, it's had some amazing successes, no doubt. We've seen AI defeat the best human players in incredibly complex games like Go and Dota.
Absolutely, those were groundbreaking achievements.
However, it's important to remember that the algorithms that achieved those feats were often highly specialized. They were meticulously designed and fine-tuned to excel at that specific game, whether it involved the discrete moves of Go or the continuous actions and team strategy of Dota.
Right. So you have these algorithms that are brilliant at dealing with a limited set of very clear actions, like in many board games. But then you have other kinds of problems, like controlling a robot, where the actions are continuous. You're not just picking from a menu of moves, but deciding on very precise motor commands.
Yeah, totally different.
And then you have tasks where rewards are really few and far between, like finding that diamond in Minecraft. You might have to perform thousands of actions before you get any positive feedback at all.
And this is the crux of the challenge. If you want to apply reinforcement learning to a new and different type of task, say moving from being great at Atari games to controlling a robot arm, it usually demands a lot of human expertise.
You need someone who really understands the inner workings of the algorithm to come in and start adjusting all sorts of settings, these things called hyperparameters. It's often a very manual and time-consuming process of trial and error.
It's almost like trying to use the exact same settings on a sophisticated sound system for both a quiet classical piece and a really loud rock concert. It's probably not going to sound great for both without some serious tweaking.
Exactly.
And the researchers behind DreamerV3 point out that this brittleness really limits how broadly we can use reinforcement learning, especially when we're dealing with really complex AI models that require a lot of computing power, or in situations where it's just too difficult or takes too long to constantly be tuning the algorithm.
Precisely.
Yeah.
This need for significant human intervention and task-specific adjustments has been a major bottleneck in the field. And DreamerV3 is a direct attempt to overcome this limitation by creating a more general algorithm that can perform effectively across a wide spectrum of tasks without needing these specialized tweaks every time a new challenge is presented. This suggests a potential shift from an era of bespoke AI solutions towards more adaptable, off-the-shelf intelligence.
So how does it pull this off? What's the core innovation that allows DreamerV3 to be so adaptable?
Well, the central idea is that it learns what they call a world model. Okay, let's unpack this. Think of it as an internal simulation, a kind of AI's learned understanding of how the environment it's interacting with actually works. Imagine how we humans often approach new situations. We don't just act randomly. We often visualize different possibilities in our minds. We think about what might happen if we take a certain action.
Right.
And what the likely outcomes could be. DreamerV3 does something similar internally. It learns to predict what might happen in the future based on the actions it takes.
And the researchers describe DreamerV3 as having three key components, almost like a brain, a decision maker, and an evaluator working together. First, there's the world model itself. As we just mentioned, this is the part that tries to predict future situations and the rewards you might receive based on your actions.
Yeah, and the world model isn't just one single block. It has several interconnected parts. There's an encoder, which takes in the raw sensory input, like the pixels from a game screen or the data from robot sensors, and converts it into a more compact and useful representation.
Okay.
Then there's a sequence model, which uses the history of past actions and encoded states to predict what that representation might look like in the future.
Right. And it also includes a reward predictor, which tries to anticipate what reward you might get in the future, and a continue predictor, which figures out if the current episode or task is likely to end soon. And to make sure this internal simulation is actually useful and connected to reality, there's also a decoder that tries to reconstruct the original sensory input from the model's internal understanding. It's like the AI is constantly trying to verify if its understanding of the world matches what it's actually seeing.
Exactly. These components, the encoder, sequence model, reward predictor, continue predictor, and decoder, all work together to build and refine the world model. The fundamental idea is to learn a compressed yet informative understanding of the environment's underlying rules and dynamics.
So it's learning the rules first.
In a way, yes. The insight that this unsupervised learning of a world model is crucial is a significant shift in how we might approach building general AI.
Then you have the second component, the critic. Now, the world model is making predictions about what might happen, but the critic's job is to judge how good those predicted outcomes actually are. Is this a path that's likely to lead to success and rewards, or is it more likely to be a dead end?
Precisely. The critic evaluates the value of the future scenarios that the world model is imagining. It's essentially saying, based on my understanding of this world, these predicted futures look promising, and those others, not so much.
And finally, we have the actor. This is the part of DreamerV3 that actually makes the decisions. Based on the world model's predictions about the future and the critic's evaluations of those predictions, the actor chooses which actions to take in order to achieve the best possible outcomes.
So you have this continuous loop. The actor takes an action in the environment, the world model predicts what the consequences of that action might be and what rewards might follow, the critic evaluates those predictions, and then the actor uses that feedback to learn and choose better actions in the future.
Okay.
And importantly, all three of these components, the world model, the critic, and the actor, are trained together based on the algorithm's accumulated experiences interacting with various environments.
It sounds like a really well-integrated system, but the researchers mentioned that getting these world models to work reliably and achieve strong performance across many different tasks has been a persistent challenge in the field. So what's different about DreamerV3 that allows it to overcome these hurdles?
That's a key question. While the idea of using world models in AI isn't entirely new, DreamerV3 introduces a set of novel robustness techniques. These are essentially innovations in how the algorithm learns that make it much more stable and effective when applied to a very wide range of different problems.
Okay, let's delve into these robustness techniques. The paper categorizes them into three main areas: normalization, balancing, and transformations. Can you give us a sense of what the core ideas are behind each of these?
Sure. Let's start with normalization. A fundamental issue when dealing with many different tasks is that the data the algorithm encounters can have wildly different scales. For instance, the pixel values in one video game might range from 0 to 255, while the readings from a robot's joint sensors could be on a completely different scale. Normalization techniques help to bring these diverse ranges of values into a more consistent and manageable range for the algorithm to process. Think of it like calibrating different measuring instruments to all use the same units.
And the paper specifically mentions something called SimLog transformation for certain types of data. What's the benefit of using that?
So the SimLog transformation is a clever way to compress the range of values, especially very large positive or negative numbers, while still accurately representing values close to zero and preserving the sign. This prevents extremely large values in the data from dominating the learning process
Oh,
and helps to stabilize learning across different tasks that might have very different input and output scales.
that makes sense. You wouldn't want a few extreme data points to throw off the entire learning process. What about the second category, balancing? What's being balanced here?
Balancing refers to ensuring that all the different aspects of the learning process contribute effectively and that no single part overwhelms the others. The paper emphasizes something called Kullback-Leibler, KL balancing,
Okay.
related to the world model's ability to predict the next state of the environment and to accurately model the environment's rules.
Okay, that sounds a bit technical. Can you simplify that for us?
Yeah. Think of KL balancing as a way to make sure DreamerV3 pays attention to both learning the underlying rules of the environment and being able to predict what will happen next. Without this balance, the algorithm might become really good at predicting, but not actually understand the fundamental reasons why things happen, or vice versa.
The paper also mentions free bits in this context. What are those?
Free bits is a mechanism, a clever mechanism to prevent the algorithm internal representations of the environment from becoming too simplistic and not capturing enough meaningful information. It essentially sets a minimum amount of information that the model needs to encode, preventing it from just finding a shortcut to minimize error without truly understanding the environment.
And then there's something called 1% unimix for categorical distributions. What does that do?
Right. So in certain parts of the algorithm, like when it's making discrete choices, it uses categorical distributions to represent probabilities.
Yeah.
The 1% unimix is a way to inject a tiny bit of randomness, a 1% chance, into all possible outcomes, even if the algorithm is very confident in one particular choice.
Okay.
This helps to prevent the algorithm from becoming too certain too quickly, and it can encourage further exploration and learning.
All right, that's a lot of fine-tuning happening behind the scenes to keep things balanced. Let's move on to the third category, transformations. How do these techniques contribute to the overall robustness?
Well, transformations change the way information is processed within the algorithm to make learning more stable and less sensitive to the specific characteristics of different tasks. The paper highlights the Simex two-hot loss used for the reward predictor and the critic.
Simex two-hot loss. That sounds quite specific. What does it achieve?
This technique is used when the algorithm is predicting rewards and the value of different situations. Instead of directly predicting a single number, it divides the possible range of rewards and values into a series of exponentially spaced bins.
Okay, bins.
Yeah, and the algorithm then learns to predict a probability distribution across these bins. The two-hot part refers to how the target value is represented. It activates the two bins that are closest to the actual value.
So instead of saying the expected reward is 2.7, it's saying there's a high likelihood the reward falls somewhere between these two adjacent bins on our exponential scale.
Exactly. And the Simex part, the exponential spacing of the bins, allows the algorithm to handle a very wide range of reward and value scales more effectively. The key benefit of this approach is that it makes the learning process less sensitive to the exact magnitude of rewards and values, which can vary dramatically from one task to another. This leads to more stable and generalizable learning. So all these techniques work together to allow DreamerV3 to use the same underlying settings across very different challenges.
That's really remarkable, using the same fundamental settings across such a diverse range of problems without needing task-specific adjustments. It really does sound like a significant shift.
It is. It represents a move away from the traditional paradigm in reinforcement learning, where significant manual tuning was often required for each new application.
Now let's talk about what is perhaps the most striking demonstration of DreamerV3's capabilities. Its success in mastering Minecraft, specifically learning to collect diamonds from scratch. The paper calls this a substantial challenge. Why is this such a significant achievement for AI?
Oh yeah, collecting diamonds in Minecraft has indeed become a kind of benchmark problem in AI research, and for good reason. Firstly, the rewards are incredibly sparse. You don't get any immediate feedback for just wandering around or breaking random blocks. You only get a reward when you achieve a significant milestone, like crafting a pickaxe, finding iron ore, and ultimately discovering a diamond. It's like trying to find a needle in a very large haystack where you only get a tiny pat on the back when you finally succeed.
So the AI has to figure out this entire long sequence of actions from the very beginning with nothing, all the way to obtaining a diamond without much in the way of intermediate positive reinforcement. It's like trying to solve a very complex puzzle where you only know you've succeeded at the very end.
Precisely. This highlights the algorithm's ability to handle complex, long-horizon tasks with sparse rewards, a challenge that mirrors many real-world problems. Secondly, the world of Minecraft is vast and procedurally generated. This means the environment is different every single time the AI starts a new game. So the AI can't just memorize a specific sequence of steps. It has to learn general strategies for exploration, resource gathering, and crafting that will be effective in any new Minecraft world it encounters.
It's not a static game board, it's a dynamic and unpredictable environment.
Exactly. And it's not just about exploring. There's also the complexity of crafting you need to combine different resources in the correct way to create tools and other useful items. There are long time frames involved. Even experienced human players can take a while to find diamonds.
Yeah, definitely.
And the overall complexity of the game with its many different elements and interactions is just immense.
Absolutely. Because of these factors, the sparse rewards, the difficulty of exploration, the long time horizons required, and the procedural diversity of the environment, previous attempts to tackle this diamond collecting challenge often relied on significant human assistance.
Right, like human data or guides.
Some approaches use data from expert human players to guide the AI's learning, while others employed step-by-step instructions, known as curricula, to gradually lead the AI towards the final goal. But the paper emphasizes that DreamerV3 was applied to this challenge out of the box. No human expert data was used to train it, and no specific step-by-step instructions were provided. It was just the algorithm with its standard settings. And it became the first algorithm, to the researchers' knowledge, to achieve this feat. That's a truly remarkable demonstration of its general learning ability.
The figures in the paper really underscore this achievement, showing DreamerV3's progress in obtaining various Minecraft items compared to other state-of-the-art methods. While some other algorithms could manage to acquire intermediate items like an iron pickaxe,
Yeah, I saw that.
DreamerV3 was the only one that consistently succeeded in finding diamonds.
It's like everyone else got stuck partway through, but DreamerV3 managed to find the complete solution. The paper mentions that they used a simplified set of 25 basic actions for Minecraft in this research. What kinds of things could the AI do with those actions?
Well, those 25 actions, detailed in the paper, cover the fundamental ways a player interacts with Minecraft. Moving around using keyboard-like commands, using mouse actions for mining and interacting with objects, controlling the camera to look around, and crucial inventory actions for crafting new items and equipping them.
Okay.
So while it's a simplified action set compared to the full complexity of human controls, it still allows for a very wide range of meaningful interactions within the game world.
And the researchers also mentioned speeding up how quickly blocks break in the environment. What was the reasoning behind that?
Yeah. In standard Minecraft, breaking some types of blocks can take several seconds of continuous interaction. For an AI that's learning from scratch, trying to randomly stumble upon the correct sequence of actions needed to, say, break a tree to get wood and then use that wood to craft tools would be incredibly time-consuming and inefficient.
Right, just waiting around.
Exactly. By speeding up the block-breaking process, the researchers could focus the AI's learning on the higher-level challenges of exploration, planning, and crafting, rather than getting bogged down in the low-level mechanics of repeatedly performing a single action for an extended period.
That makes perfect sense. You want to test the AI's ability to strategize and solve the core problem of finding diamonds, not just its virtual patience. So, looking beyond this impressive Minecraft achievement, how did DreamerV3 perform on those other diverse benchmarks you mentioned earlier?
The paper presents a pretty comprehensive evaluation of DreamerV3 across a wide array of benchmark tasks. And the results are very encouraging across different domains like Atari games, these procedurally generated levels in ProGen, the complex 3D environments in DMLab, and various robotic control tasks. DreamerV3 consistently performed at the level of, or even better than, the best specialized algorithms, those that were specifically designed and tuned for each individual benchmark.
Wow.
This really highlights the potential for more general AI that doesn't require task-specific expertise for every new problem.
That's a really powerful result. So this single algorithm using the same set of core settings is competing with experts in all these different areas and achieving top-tier performance.
Exactly.
Yeah.
And perhaps even more significant is the comparison they made to PPO, which stands for Proximal Policy Optimization.
Okay, PPO, right.
PPO is a widely used and highly regarded reinforcement learning algorithm known for its robustness and good performance across many different tasks. DreamerV3 outperformed PPO across all these diverse areas, again, without any task-specific hyperparameter tuning.
That's huge.
This suggests that DreamerV3 isn't just good, it's demonstrating a new level of generalization in reinforcement learning.
So it's not just beating the specialists, it's also outperforming a very strong generalist in its own territory. That really speaks to the power of the underlying approach. What about how well DreamerV3 scales? If we use more computing power and build larger models, does it tend to get even better?
Yeah, the researchers also investigated how DreamerV3 performs as the size of the model is increased, and the findings are promising. They trained versions of the model with different numbers of parameters and observed that larger models generally achieved better performance and, importantly, became more data efficient.
Okay. Data efficient.
Meaning they required less interaction with the environment to learn effectively. This suggests that with greater computational resources, the capabilities of algorithms like DreamerV3 could continue to improve.
So by investing more in computing power, we can expect to see even better results with less actual trial and error needed in the real or simulated world. That sounds like a very beneficial trend.
It is. They also looked at how often the algorithm revisits and learns from its past experiences, a concept called the replay ratio. They found that increasing this ratio further improved data efficiency. This indicates that effectively utilizing past learning is another key factor in enhancing the capabilities of such algorithms.
Now, the researchers also conducted something called an ablation study to better understand which parts of DreamerV3 are most critical to its success. What were the key insights from that?
Right. In their ablation study, they systematically removed or modified different components and learning signals within DreamerV3 to see how these changes affected its performance. One of the most interesting findings was that DreamerV3 heavily relies on the unsupervised objective of its world model.
Unsupervised objective. What does that mean in this context?
It refers to the world model's primary goal of learning to predict and reconstruct the environment it's interacting with, without direct feedback from task-specific rewards.
Okay.
The ablation study revealed that this aspect of learning a general understanding of the world was more crucial to DreamerV3's overall success than directly learning from the rewards of the specific tasks it was trying to solve.
Wow, really?
Yeah, it's like the AI first builds a foundational understanding of how the world works, and then it can leverage that understanding to tackle specific challenges more effectively.
That's a really profound insight. So it's almost like by developing a good internal understanding of the fundamental rules and dynamics of the world in general, the AI becomes much better at solving specific problems within that world, even when the rewards for those problems are few and far between.
Exactly. And this suggests exciting possibilities for the future of AI. Perhaps we could pre-train these world models on vast amounts of general, unlabeled data, like videos of the real world.
Right.
And then apply that pre-trained understanding to a wide range of specific tasks, much like how humans use their general knowledge to learn new skills more easily.
So to summarize, DreamerV3 appears to be a really significant leap forward in the quest for a truly general AI algorithm. It has demonstrated the ability to master a remarkably diverse set of tasks, from playing classic video games to controlling robots to even figuring out complex challenges like collecting diamonds in Minecraft, all without requiring extensive human intervention or task-specific tuning. This suggests a future where AI could be much more adaptable and applicable to a wider range of real-world problems.
That's the core message. Its success in tackling incredibly complex tasks, like finding diamonds in Minecraft from scratch, really highlights its potential to address challenging real-world scenarios with minimal human guidance.
Yeah.
Consider the implications for fields like robotics, automation, and even scientific discovery, where an AI could learn to navigate intricate systems and achieve goals without needing to be explicitly programmed for every single possibility.
And for you, the listener, who's interested in gaining knowledge quickly but thoroughly, I hope this deep dive has provided you with a clear understanding of this cutting-edge AI achievement and the fundamental principles that underpin its remarkable capabilities.
This raises a compelling question for us to consider. Could algorithms like DreamerV3, by developing these rich and general models of the world, eventually achieve a form of general intelligence that allows them to learn and adapt to entirely novel situations. Challenges we haven't even imagined yet. It's a fascinating prospect and something to really ponder regarding the long-term trajectory of AI research.
Absolutely. If you're interested in exploring this further, we highly recommend checking out the original research paper, Mastering Diverse Control Tasks Through World Models, or looking for the open source implementations of DreamerV3. There's a wealth of technical detail there for those who want to dive deeper.
But for now, it truly feels like we've only just begun to scratch the surface of what might be possible. This feels like a significant step towards a future where AI can learn and adapt in ways we're only just starting to understand.